Hey guys, we're just gonna go over the solutions for BigO notation. BigO asks the question, how does our algorithm scale with input size? So you got the O here, and we pretty much put our input here, pretty much saying exactly that question. How does it scale with input size? So we know from the assignments or from the research and the links that you were given, you guys should know by now. Some of the easy ones are, or the most common ones, constant time, linear time, and polynomial time. Constant time is the best one, best we could do. It's 1 because when you put in a function, let's say f of any function, if the y value is a straight line, it doesn't move, it doesn't go up or down. So you can have an array of 1, or you can have an array of a lot, millions and millions, and it would still run at the same speed, which is fantastic. So I made 2 arrays here. The second one is going to be used more for the polynomial BigO, but I wrote the code already. I'll just comment it out as we go. And we're going to do node. Hopefully you guys are a little bit familiar with node. I don't know if you guys are going over it yet, but we'll do node, BigO. And what we're going to see here is I'm running this on array 1. So this constant time here is just an example of this is an array index. The array, we know that it's stored in memory, and when I say array 2, it should output 6. 0, 1, 2, and we're going to get 6. This is constant time because the array is stored in memory, and when you index it, the computer knows exactly where in memory this is because it knows where the array is. This is the variable, and it's going to just do its offset. This is just an offset, so it knows exactly how to get that really, really fast. And that's why arrays are really good for storing sequential memory. Okay, and we'll get 6 here. I put a line break in after. I don't know if you guys have ever seen that before, just for for readability. Again, let me save this. Again, we're gonna run it here. This is with the second D array. So if you guys want to pause the video and guess what's gonna come out here, well, I kind of just highlighted it there. So, but yeah, it's going to be this whole array, 10, 11, and 12, because this is a 2D array. That's why I wrote 2D. So rainbow brackets makes it really easy. Boom and boom. You got the purples are the inner brackets. And this is actually just a matrix. I'm going over linear algebra now in my schoolwork. And yeah, it's just pretty much a matrix. So a 3x3 matrix. So it's another way to look at it if you guys like it that way. Okay, we're going to do, let's comment this stuff out. Well, we need the arrays. We're going to do the linear time function, so O of n. That means big O is going to scale with input size. So an example of this is just iterating through pretty much, it's one for loop. It's going to iterate through the array, and that's going to, so now you know that this iteration, if the array size is 1,000,000 long, it's going to have to go through 1,000,000 times and console each index out 1,000,000 times, that's obviously scaling with its size. We got to call the function to run that, and this is actually on the 2D array, so it's outputting all the indices. So this is index 0, index 1, index 2, because the indices actually are arrays. If that's confusing for you, we can also do it with this. Clear that. Oh. Run it like this, and this should just be 2, 4, 6, 8, which is the first array. Right? Same thing. Polynomial time. It's not great. It's n squared, so that means it's going to do it twice. So that means for every n, it's going to run, it's going to go through it again, and it's going to go through another n, which is n squared. So let's see how this one works. This is why pretty much I made the 2D array. So here, scroll up a little bit. Polynomial time. So now this is 2 for loops. I'm going to loop through it once and loop through it again. Here, the second for loop actually iterates through the index of the first position. So let's call that, and it's going to loop through. Now it doesn't loop through the array. It doesn't give an array like you saw the first time. It actually just goes through each one: 14, 15, 16, 10, 11, 12, 20, 21, 22. It's going to go through them sequentially. Each one sequentially. I mean, this is all just implementation. It's just an easy way to see this. You know, the most simple example of this stuff. There's a lot more big O notations. There's logarithmic, exponential, which is really bad, and that's a lot of stuff that it's good to know. It's good to know what big O does. And here, actually, just a tip for big O notation. It's pretty much how many for loops, nested for loops. If I put another for loop down here, if I were to put another for loop right under here and say for whatever, let blah blah blah, this would be O to the O(n) to the third, because it's looping. It's going through 3 times. So that's a good way to see nested for loops is what your exponent's going to be. One more tip is that if you have, let's say, look at this function. If you have a for loop here and then a for loop down here, and it's the same thing, if you just copy this twice, this is actually still O of n. You're going through n because this becomes 2n, right? But with big O, we just drop any constant scalars in front. So, you know, a function that takes 2n, it just literally becomes n. So 2n is really the specific way to say it, but we get rid of the 2, we drop the constant, and we just worry about the n. So if there's a lot of for loops like this, yeah, realistically, it would take longer than just one for loop, but for big O terms, it's kind of simplifies to just n. So there you go, guys. Cool. Hope you enjoyed that.